Okay, so tomorrow we're going to write our Unit V test. So this will be on chapters 10, 11, and 12. So 10 was like standing electric charges, right? When things are just kind of stationary, not moving, right? Chapter 11 was electric field theory. So that's where we had like our resistance and our current and some voltages and stuff like that. And also accelerating charges when they're entering parallel charge plates, to name a couple, okay? And then last chapter we just finished was electromagnetism, okay? The relationship between electricity and magnetism. Okay, I included some momentum on here because the final is going to be cumulative, right? So I think it'll be good to just kind of sharpen our momentum saws. Okay, so anytime that we have momentum, what was like the really big idea in that unit? Perfect. So yeah, so momentum in equals momentum out, right? So like sum of momentum in equals the sum of momentum out. The law of conservation of momentum, right? In a completely isolated system. Okay, so in this case, it's a firework, which is initially at rest. So what is the momentum going to be if it's not moving? Zero, right? Because remember, momentum is equal to mass times velocity. If our velocity is zero, we have zero momentum, right? So going in, we have zero momentum. And going out, this firework is exploding into three pieces. So we're going to have the momentum of 1 plus the momentum of 2 plus the momentum of 3. Okay, so that's how we set it up. And now we'll just write down our variables, what we know. So the mass of the whole bundle is 0.5 kilograms. And it's going into three pieces. So fragment 1, so M1 is 0.2 kilograms and has a speed of 3.7 meters per second. The second fragment has a mass of 0.15 kilograms and a speed of 2.9 meters per second. We're asked, what is the speed of the third fragment? Okay? And we can calculate the mass of the third fragment by subtracting the first and second fragment from the total mass. So 0.5 kilograms minus 0.2 is 0.3, minus 0.15 is 0.15 kilograms. Okay, so now that we have all of this, we will just solve for our V3. Okay, so remember, this will go M1 V1 plus M2 V2 plus M3 V3. We are looking to solve for V3, so you will subtract M2 V2 and M1 V1 from both sides. And then we will divide by M3 to get our V3. So the velocity of the third fragment is equal to negative M2 V2 minus M1 V1 over M3. 2.5. Divided by M3. What did you guys get? And remember, if we get it in a negative direction, that's just saying that it's going in like the opposite ways of the first two fragments, right? So I got negative 7.8 meters per second. Confirmed? Okay, so this is just saying that this is going in the opposite direction as the first and second fragment. Okay? So again, I think the really big and important part is just remembering that the sum of momentum going in must equal the sum of momentum going out, right? Okay, so you'll see a question like this, something exploding, and you're also going to see a train running into a stationary train, and then they're going to continue moving with one another. Okay?
What's that type of question called?
Hit and stick. Nice. Nice, Sam. Excellent. Hit and stick.
Will we have to, like, for the explosion one, is it just going to be speed, or is it going to be velocity? Like, will we have to find the degrees of angles?
No, it'll be pretty similar to this one.
Okay, let's see.
Okay. All right. Any other questions regarding momentum?
What were the other kinds besides hit and stick?
Hit and not stick. No, don't worry too much about the types. But we had 4, right? We had an explosion, hit and stick, a rebound, and what's the last one? Something like that. I'd have to check the notes.
Are we supposed to know how to do each book?
Not for tomorrow. Not for tomorrow. Just know the hit and stick and the explosion. Yeah. All right. Okay. So remember way back in chapter 10 when we did our Coulomb's law lab / calculations, right? Do you guys remember this? We were given the dy and the dx in the lab itself. And then from that, we were calculating the electrostatic force on the sphere, right? Because we were changing the charge of the one sphere and we were changing the separation distance between the spheres, right? Okay, so we noticed as we increased the charge, we increased the electrostatic force, right? And as we increased the radius, we decreased the electrostatic force, right? That's all good? Okay, so remember that, please.
And FG is mg?
Yes.
Okay.
Yeah. FG is mg, okay? And yeah, so we can indirectly measure the electrostatic force by finding the rate of change of y and x of our system, okay?
Will those be given to us, or like we're gonna have to?
Yep.
We're gonna solve for them.
You'll be given enough information
Okay.
to solve it, okay? I'm just telling you guys, brush up on this type of problem, okay?
Sweet.
For sure, okay? Because I am not going to tell you this tomorrow, so make sure you remember dy over dx is equal to fg over fe, okay? This is the law of similar triangles, okay? So make sure you guys remember how to do that, okay? dy over dx is equal to fg over fe. And yeah, this PowerPoint is on the Google Classroom too, so don't worry too much about like writing everything down, okay? Or I can print them off after this if you'd like. Okay? Okay, so yeah, anyways, so we have electrostatics, right? So we can go through this one. So this is the electrostatic forces, and these are not moving charges. Okay, these are stationary charges. So what formula are we going to use for this type of a problem?
Wait, isn't it like F net of A equals F of B on A plus C on A?
Perfect. Okay. Okay. Yeah. So that's your net force equations, I guess, right? So we are concerned about A, right? So F net A, and I guess we should be, I don't know, the FE net, right? The electrostatic net force at A is equal to the electrostatic net, well, Fe of B on A plus the electrostatic force of C on A, right? Fe net A is the electrostatic force of B on A plus the electrostatic force of C on A. We're good? Okay. So how would I calculate the electrostatic force of B on A?
The Coulomb's law?
Yes, Coulomb's law. Okay, Coulomb's law. So Fe is equal to K times Q1 times Q2 over R squared. Okay? Use Coulomb's law. Okay, so, and then yeah, you guys can choose whichever one you decide to go do first. Just remember that we have, well, you guys tell me, what's up with our charges? Are they all the same? They're different, Peyton says. I agree, right?
I grow pack.
Charges, right? -5, +3.
Oh, I thought you were talking about like units like millicoulombs.
Oh, no. Sorry. No, just the charges itself. The degree, yeah, the signs of the charges, right?
Yes.
So positive and negative, right? What happens between positive and negative? They're going to attract, right? Yeah, they're going to attract for sure. So is this one going to be pushing it away? Or is it going to be pulling it down?
Pulling it down.
It's going to be pulling it down, right? I always like just drawing those arrows because it just helps me kind of conceptualize what's going on there. And then what about this one here? If we have two negative charges, is this going to be attracted over here? No, it's going to be pushed the other way, right? Yeah, so this is going to go down and this one's going to go right. We should expect it to go something like that, right? Okay, in this question I just care about the magnitude, not the direction. And tomorrow, it's not going to be a resultant one. Okay, it'll just be a straight line one tomorrow. Okay, so if you can get through this, you'll be totally fine. Yeah, let's go through this. Okay, so let's do B on A. Okay, so FB on A is equal to K, which is 8.99 times 10 to the negative 19? No, positive 9. What am I thinking of?
That's the electrode.
Thank you.
Electrons.
Thank you. Okay. Maybe I'll write that down just so we can remind myself. So K is 8.99 times 10 to the 9 coulombs. Q1, and this is B on A, so we have 3 times 10 to the negative 6 coulomb. Remember, a microcoulomb is equal to 10 to the negative 6 coulombs. Okay, so 3 microcoulombs is 3 times 10 to the negative 6. multiplied by 5 times 10 to the negative 6 coulombs. I just realized that I didn't do my units right for my constant. 8.99 times 10 to the 9. What do we got? Newton meter squared per coulomb squared. Good. And then we're going to divide that by our separation distance, which is 4 centimeters, which is 0.04 meters squared. Okay? And what do you guys get? What do we get? $84.28. Yeah. So 84.28 newtons. What? What? Wait. That is pushing it to the right, correct?
Can you just put like repulsion too?
It's alright.
Yeah. I mean, you could if that's fine for you. Yeah. Okay. So then you do the same thing for the next one. This is 4 centimeters, and our charges are just the same, right? 5 times 10 to the negative 6, 3 times 10 to the negative, other than us pulling it down, and so we should get the exact same number. So force of C on A is going to be 84.28 newtons down. Okay, so I'm just going to jump over to the whiteboard here. Right, so we're pushing it to the right, 84.8, and it's going to the down of 84.228. So our resultant is going to be right here. And what do we want? Square that times 2. And what did you guys get? 119?
Wait, so are we not using the B on A plus C on A? Because then it would just be 84.28 times 2, right?
Okay, so, but is what we have here, we have one in the horizontal direction,
Mm-hmm.
right? And one in the vertical direction.
So then we need to do that.
We need to find our resultant vector.
Okay.
Yeah, because B is pushing A to the right,
Mm-hmm.
and C is pulling A downwards, right?
Okay.
So this is A on C, or C on A rather. And this is B on A. And this is just our F, E, net there. So C is going to equal the square root of 84.28 squared plus 84.28 squared. Yeah. $119.22, yeah. And then we got FE net, A is equal to 119, well, that'll be it. So 119 newtons. And if I asked you, you would find your displacement, right? Like you would have to find your angle here, your direction of your displacement. Okay, but in this case, I forgot to change that too, but I just wanted you guys to find the magnitude of that, okay? And then when you go tomorrow too. Yeah, you're just gonna be finding the magnitude because it's and direction actually.
Would you only use FE of B on A plus FEC on A if they were both horizontal?
Yes.
So
If-
it doesn't really apply for this one, you just have to use the triangle.
Yeah, because one's an X horizontal component and one is a vertical component, right? If they were all
So we can-
in line like this, then it is all going to be horizontal, right? Is that good, Aaron? Yeah.
So then that from the top is just kind of to show us what we need to calculate.
Yeah,
In
exactly.
order to get to.
I always like to just do this formula here because it just shows me, yeah, like you said, like what you need to calculate, and it just kind of like draws that picture a little bit more descriptively. All right. Okay, so again, just don't forget about this, right? So we did the Coulomb's law investigation and we made the graphs and calculated K. We indirectly measured the electrostatic force by calculating the ratio of how far the sphere moved in response to changing the separation or the charge, okay? And this was our image, the law of similar triangles, to help us find the electrostatic force there. Okay, now from that information, okay, you guys are going to be given a problem similar to that. And then, so you will need to know how to calculate your electric force, right? From that last formula that we just talked about, okay? And then I also want to draw attention to the tension in the string. Okay? So the tension in the string is a resultant of what? Or not a resultant, but like and what? So gravity? Nope. So no, gravity is good. And what? And the electric force. So it's like it's the hypotenuse, right? So it's like related to both of them. So when you're calculating the tension in the string, please do not just calculate the force due to gravity and say that is the tension of the string. Okay? Please do not do that. Tension in the string is the hypotenuse. Okay?
Gravity and electric.
Of both of them, yeah. Because think of it this way, right? So if I'm holding this mask, what is the tension in the string from? Just right now. It's just from gravity, right? But as soon as I start moving it around, the tension in this string is from gravity and the force that I'm applying to make it move in a circle, right? We wouldn't just say the force of tension is just the weight of it, right? It's the weight of the thing plus the motion of it. Does that make sense? So tomorrow, do not just calculate the force of gravity of the thing on the string and say that that is the tension in the string, okay? Fair warning? Okay. Good. Okay. I keep losing this here. Okay, so remember, electric fields are uniform between parallel plates. So just in summary, the magnitude of parallel charge plates is uniform and does not vary. Okay, so what you have up here is going to equal the same thing down there, right? It's constant throughout the whole plate. Okay, there's not regions that have like different charges. There's not pockets of different charges, is what I'm trying to say, right? We have positive at the top, so the electric field is moving down. It's going to be stronger at the top and weaker as we get to the bottom. Okay, this is where it's just generated, right? So it's going to decrease with distance. Okay, so make sure you are able to recognize this formula too on your formula sheet. Okay, the parallel plate formula. Okay, make sure you guys brush up on our formulas. Okay.
Wait, can I like double check to make sure I have the right one?
Yeah, please.
It's doesn't like that to be a really good one, right?
Yes.
Okay.
E is equal to delta V over delta D, this guy right here. Bottom left corner of your electricity and magnetism formula sheet. Okay. So if we want to move a particle through a electric field, we need to apply a force, right? And that force, Fe, is equal to E times Q. Okay, we need to apply a force. Wake up. Oh, there it is. That's it. Yeah, so note that E is, so energy or electric field strength is often expressed in volts per meter. And again, don't get tripped up with our units, because a volt per meter is equal to a Newton per Coulomb. Okay, I will leave our fundamental units up there for tomorrow. Okay, so just just know how to use those. Okay. Okay, know about the motor effect force. I feel like you guys should be really, really good with this stuff. You guys got lots of chapter 12 practice, right? Okay, so yeah, this is the deflecting force acting on a charged particle moving in a magnetic field. And this requires the interaction of two magnetic fields to deflect that charged particle. And the interaction between the magnetic field, so the interaction between the magnetic field produced by the moving particle and the external magnetic field produces a magnetic force that acts on the particle to deflect it. We call that the motor effect force, and that is kind of the idea behind electric motors. Okay? Okay, know how to use this formula. So Fm is equal to QVB or BQV. I'm pretty sure it's QVB on the formula sheet, right? So QVB, yeah, that's right. That's right. B is the magnetic field strength. Fm is the magnetic force. Q is the charge. V is the velocity. And if it's not moving perpendicularly, then you have to use sine of theta. Yeah, I am not going to say anything about that because I can't remember. There might be one on there that's at an angle, but if that's the case, you just use this formula, right? And you guys had a question like that in your practice problems too, so fair game. Okay, know which direction the particle will be deflected as it enters a magnetic field. Okay, so if it enters parallel with the magnetic field, there will be no deflection. If it moves perpendicularly, it will move it into, it'll just kind of keep deflecting it up and down, right? If it comes in on a degree, it will move in a spiral. And then in that case, when it does move into a spiral, we say that centripetal force is caused by the motor force, right? So Fc is equal to Fm.
Wait, that formula is Fc equals mv squared over r?
This one, right?
Yeah.
Yeah, so yeah, exactly. So when a charged particle is moving in a circular pattern in a magnetic field, the result of that, or the force causing that particle to move in a circular motion is the motor force. Okay, so we see that the motor force is the centripetal force. Motor force is QVB or BQV, and centripetal force is mv squared over r. Okay, this right here is not on your formula sheet. Okay, so you need to know how to get to there from nothing. Actually, I shouldn't say that, because you do get some information, right? You get AC is equal to V squared over R? No, that's wrong.
That's right.
Is it?
Yeah.
Okay, good.
Wait, where?
So centripetal acceleration is V velocity squared over R. So you get that on your formula sheet, right?
It's in the kinematics section.
Yeah.
Oh, kinematics. kinematics?
Yep,
Wait.
right here.
Oh.
Yeah. Yeah, so you get that. So it's in the kinematics, so that's physics 20. Maybe a review, maybe not. We went over it in class anyways.
Yeah, yeah.
So we get centripetal acceleration is v squared over r, and we know that force is equal to mass times acceleration, right? Right? So if we want to find the centripetal force, it'll just be mv squared over r. Okay? Are you guys okay with this? Yeah? Okay. Okay, so make sure you know that, and then, yeah, you get QVB is equal to FM on there. Okay? So make sure we know this. This is a need to know. And then that just simplifies to that because your velocities cancel. Yeah, so we can use this equation to find any unknowns pertaining to charged particles moving in a circular path in magnetic fields. Kind of like those experienced by the Northern Lights, right? Okay. And that's just a fun picture. Not related, just circles. Circles and circles and circles. Okay, electromotive force. So remember, electromotive force, was this a quiz question or a practice problem question? I don't remember. But it was one or the other. You guys have had a practice problem for this, okay? And this is the increase in energy the electrons in the wire experience when they are moving, right? When they're moving. And this can be calculated as follows. So EMF, electromotive force, is equal to voltage, 2, right? Which is equal to BVL, which is magnetic field strength, times the length of the wire inside of the system, times by the velocity of the moving, okay? Or you can get delta E over Q, okay? Change in energy over Q there.
So if it asks you for the electromotive force, you should just like automatically be like Q for V.
And that's going to be voltage, right? So electromotive force is in voltage, okay? Yeah. And that's just saying like...
Am I looking for the variable V? Yes, right?
It depends on the question, right? So like B is magnetic field strength, right?
Yeah.
And then L is length of wire, so it just depends on like what kind of
What's
what you're given in the question. Yeah.
Okay.
Aaron?
What's the difference between like? Can't remember.
Okay. We'll come back to it if it comes back to you, okay?
Wait, one more thing.
Yep.
Okay, so the electromotive force, isn't that just like the change in V? Is it not?
The electromotive force. Which one were you pointing to?
V, like V equals EP over Q.
This one here?
Yeah. Isn't like that just the change in V?
Yeah, and this would be like the change in potential energy too, right?
Okay.
Or the change in energy, yeah. Yeah, so, yeah, just be aware, like, when it asks for, like, a voltage of a system, you can calculate the electromotive force, too, right? Yeah, so just remember that, like, yeah, to find the voltage, find the electromotive force, which is this formula here, okay? Okay. Okay, forces on currents in magnetic fields. Oh yeah, I have your guys' quizzes, too. Yeah, Susanna.
Like going back to the last slide, so electromotive force is measured in volts?
Yes.
Okay.
You're like, but why?
I want my newtons.
You had yours in newtons?
No, I just need like force in newtons.
Oh, okay, gotcha. Okay, so
It just feels weird.
so electromotive force, think of like the force of the electricity itself. The force of the electricity, okay?
Alright.
Which is in volts. Does that help? Yeah.
I feel like I get messed up with all the E's. I know, there's do they like EP, E?
Because there's EP, and then sometimes there's the delta E, and sometimes there's the E with the vector on it, and sometimes there's the absolute value of E. Sometimes it means energy, and sometimes it means like electric field strength, and sometimes it means other things.
We want more variables.
So
Physics 30. Yeah.
the E's.
There are a lot of E's. There are a lot of E's.
Which ones can like be used to find other ones and which ones can't?
Who's invented
Like
like
equal.
Like for these ones, this I can use this to find like this stuff, and you put this one into this.
Except for I don't think you can use this with the parallel plates.
Yeah, but like, do you know what I'm saying? Like, can you use like this
This
one, these ones, and
I don't
use
think
like
so.
this V?
Parallel plates,
No,
one?
this V, this V, and this V.
Yeah.
Unless you can't. But like, do you know what I'm saying?
Yeah.
Like, unless you I never know which ones can be used for each other and which
I don't think there's any like honestly like tricky questions for tomorrow.
For like theory, you mean?
So I was just like talking about
Oh.
Yeah, about like which formula to use like that. Yeah, I don't. There's not like really tricky questions. I'm like, I think it's pretty fair, and I thought I was pretty clear in some of the questions. So.
Okay.
Okay, so you guys need to know what is going to happen on wires when it's in a magnetic field. Okay. So if we have a magnetic field, current carrying conductor, if we have our, well, what direction is the current going in? Is it going towards us or coming away from us if the force is moving upwards? Peyton? Into the board? Yeah, right? Good. Because we have, so our thumb will be a direction of the movement, right? And then our wrist is north and our fingertips are south. So it must go like this, right? For the force to be pointing upwards.
Wait, but if it's current, shouldn't it be the right hand rule?
Okay, well, current carrying conductor, so it's just like what way would it be flowing, right? So, okay, fine. So electrons are moving into the board, current's coming out of the board.
Okay.
Okay, and on that note, I was really clear on the test of what I'm looking for, whether it's electron flow or current flow. So,
Okay.
I'm,
Bold it, highlight it.
yeah, pretty much.
Underline.
Pretty much, yeah. So I tried to be as clear as I could. Okay, so make sure we know our left hand and right hand rules. Quinn, really good point there for
Okay.
sure. Yeah, that's good. That's good. Okay, and this is the last thing that I will talk about today. I'll give you guys the other half to review. Okay. So if current is flowing perpendicular to the direction of the magnetic field, the force produced on the wire will be perpendicular to both the direction of the magnetic field and the electron flow. Okay, so if electrons like moving this way and the magnetic field's going that way, it perpendicular is up and down to that, right? We're going like this, and then we're going like this. That is still perpendicular, right? We agree on that?
Yeah.
All right, cool. Yeah, the force direction may be obtained using the third left-hand rule. So if it's like this, right? Well, yeah. So if electrons are moving into the board, current moving out, then it would be pointing up, right? Like so, and then magnetic field is going that way. Okay? Now let me ask you guys a question. If the magnetic field is moving left to right, so opposite, okay? So wait, left to right. No, sorry, you're right. So left to right, and the wire is lifted upwards. Okay? What directions will electrons flow in the wire? And consider what part of the wire is in the magnetic field. So what directions will electrons flow? So the wire is lifted upwards. Magnetic field goes left to right. What way will the electrons be deflected?
Deflected? Or
Isn't the force just
What directions will electrons, or what direction will electrons be deflected in the wire? Or which way will electrons flow in the wire, right? Because when we put this into a magnetic field, the magnetic field is going to like push those electrons, right? right? We're okay with that? Okay? So what direction are they going to flow? What way will they be pushed? If the wire is lifted upwards and the magnetic field goes left to right, where are those electrons going, Susanna? Towards us, right? So electrons are going to come here, right? And they're going to be deflected that way. And they're going to go out in that way, right? So anytime you get a question like this, you need to look at what part of the wire is in the magnetic field and what direction those electrons will be deflected, okay? Because these are going to get deflected and then they're going to push everything else in there, right? Like think of like if you put water in a pipe, like if you put it up here, it's going to be pushing everything that way, right? If you apply pressure and push it that way, then the water is going to move this way around that pipe. Does that make sense?
How did you use your left-hand rules to do that?
So we're lifting, so the motion of the wire is our thumb.
I thought if you do it the upward force though, and then you go, because when it's moving, the way I did it was left to right, so south to north, because the field always goes south to north, right?
Okay. Yeah, but let's just forget about the force. Forget about the force on here. I should have blocked that off. Forget about the force. We're just lifting the wire, right? We're just lifting the wire. Okay, so we're just lifting the wire upwards. Magnetic field is like this. Okay, like just forget about that force. Okay, it's the direction of the. So.
It worked exactly the same.
That.
I still got that page. Wait,
So thumb,
it goes south to north,
direction of wire.
right? And then this is the force if it's moving up.
Wrist.
Okay.
So I still got that page.
Oh, because electrons go south.
You got out of the page?
Yeah, I did it that way and I still got the page.
Okay, great. Are we okay?
Thumb. Wait, do it how you were doing it though. Thumb is the direction of the wire.
Yeah. Wrist is direction of magnetic field. And palm is direction of deflection. Okay?
Wait. So then the thumb. Wait, why is the wire going up?
Because
Because it's getting lifted up.
Yep. Yeah.
Oh, okay.
Yeah. So we lift up the wire, magnetic field goes like that and it comes out at us.
And a magnetic field, does it go from north to south or south to north?
Electrons flow from south to north.
But then a magnetic field is north to south?
Are you talking about the actual magnetic field itself?
Yeah.
Okay, yeah. So yeah, magnetic fields go from north to south. Like this.
Okay.
And then remember our Earth is a big liar. It's this. Out of the north and into the south. Okay? Susanna, did you have a question?
No.
Okay.
Just looking at something.
Okay, and that's it.
Okay.
That's it. Okay?